and let's
Yeah.
turn on those webcams. Hello, everyone. Gravity Max here, back with another.
And 128 seconds.
Yeah, today, we don't have a guest. We don't need a guest today. Yeah, we don't need a guest every time, guys.
The audience is our guest.
Yeah, you guys are our guests. So today is an interesting topic. We're talking about relativity. And how are you all doing today? Are you doing good, Sebastian? Doing well, I guess, for all the grammar.
Um, yeah, I've had an interesting day.
Hmm.
You know, I was asked to deliver a mallet to a friend of mine. So I was walking down the my street in nothing but Adidas slides with a mallet in my hand, whistling and lackadaisically like swinging it.
Nice.
This guy was mowing his lawn and he sees me and he's like, "Well, the lawn's done." You know,
Yep, yep. That's. Um.
yeah. We'll make sure our audio is good while you keep talking.
Oh yeah, yeah. That's what I'm checking on. Yeah. So I'm a little tired today. Sebastian knows why. Okay. So I'm a little bit mad at myself.
We're
Basically,
good.
we're good. Okay, cool. What I did was okay. So I stayed up all night last night because I was intending on like doing work because basically this is hell week right now. Everything is due this week because like school ends on Friday for me, um, which is
Lucky.
very early, but like pretty much school was meant to end next Friday, but then they got rid of finals. So now they end this Friday, but like all the projects and stuff are due, and I haven't been working on them enough. Um, yeah, I'm not very productive. Well, I'm productive in the wrong ways, I guess, because
Yeah.
what I did last night, instead of doing my work, is I wrote 25 pages into a novel that isn't even part of like my novel trilogy that I'm trying to like publish right now. So like it wouldn't even be published for like, I don't know, 2 years at the least, right? So, and now I have 73 pages of this novel, and it's pretty good. And like my mind keeps spinning about it because it's like so fun to write. And I'm like, if only I could get as enthralled in my schoolwork as I do in this. So yeah, so I pretty much like crashed at 7 a.m. Then I've been sleeping until like 3. Now I'm awake, and right after this, I'm just gonna go back to sleep. Still haven't got like any schoolwork done, which like is not ideal, but whenever I wake up, I guess I'm just gonna have to do that. I have like I'm pretty much saying I cannot like procrastinate in any way. I am not allowing myself. I must either sit in place and do literally nothing or do schoolwork. That's the best way to force yourself to do something that you don't want to do, so you don't let yourself do anything else. You allow yourself to do nothing, because it's hard to force yourself to do something. But like you say to yourself, okay, you either do this or you just sit in place.
Yeah. I have you to hold me
Oh yeah?
accountable to not procrastinate on my novel.
Oh yeah, do you have enough
I,
pages?
I have to have 50 pages by the end of today.
Oh, the end of today.
The end of today.
Let me just check. Let me just
Oh, go
check
ahead.
how
Yeah,
many
no, go
pages
ahead.
you have. Okay.
But the thing is, I'm in a very good spot. I had to get past a spot which it was the end of a chapter.
Okay.
And once I got past that, now I'm in the new chapter. And the easiest part to write of any chapter is the beginning.
Oh,
So
that's good.
you might notice that I seem to be far off from the 50 pages.
Okay.
But
Check.
it's going to be done by today because this is going to flow like butter.
All right.
Yeah.
Let's see. So you needed 50 pages at the end of today. And opening up the document. Oh yes, and it's on night mode, which is wonderful. If you guys ever want to turn a Google document into night mode, you're able to if you go to page setup, you can make the pages black and then make the text white. Just don't try and print it like
Oh, yeah.
that. That would be called, I don't know what that would be called.
Printer murder. First degree printer murder.
All right, you got 43 pages. All right.
43. Yeah, but these next 7, Done.
Well, hey, you can always go on a all-night bender and write 25 pages, right? So,
Yeah, sure.
oh gosh, I don't know why I did that. I mean, I kind of know why I did that.
You have an issue, Max. We're gonna have to have an intervention.
Yeah, an
You gotta stop
intervention. You
writing
got to stop
books.
writing. Oh no. Yeah, I've got a bit of a writing issue. I don't know. I've heard it called productive procrastination, which is basically that like you're doing something that's technically productive because you're like doing work, but at the same time you're procrastinating on like the things you really have to do. So, I don't know, I'm just tired. So let's talk about relativity for a little bit.
Oh yeah.
Yeah, all right.
I
So
don't even have the presentation open.
fun times. This is a good day. No, the sheer like look of relief, it'll be like night and day. Next week, I will be done with school for the year. It'll be Sunday. I will be 2 days post schoolwork, and you will see me so relieved, okay? I'm like blood sugar, like or blood stress, whatever, pressure. Yes, that one. Blood
I can't
pressure,
be the smart one here, Max. Come on.
blood pressure in my blood. It's probably very high right now. And, that's not good. Stress is not healthy. So next week, you will see me a lot more relaxed. So this video is not intended for children under 13 years old. If you are under 13 years old, please do not watch this video, as the topics we discuss are meant for those with at least a high school level of education. If you are not 13, you will not understand the scientific topics discussed in this video. So the question is, if someone went on a spaceship that's like moving at light speed or like very close to light speed for 13 years, right? And they come back, and so they're only like, 1 year old. They're still like an infant, but they were born 13 years ago. Are they allowed to watch this video? The world may never know.
I'll allow it.
You'll allow it?
I'll
I don't
allow
know.
it.
What's the
If
government's
they can prove
policy?
it, if they can prove it, I'll allow it.
What's the government's policy on time dilation? I guess
Let me
I'll email does
time dilation
does the Senate have an
legality.
email account?
Uh, I
Can you
think.
just email the Senate?
uh,
I bet the Senate's email account is like, uh Emperor
time
Palpatine.
dilation legal definition.
Legal definition. I don't think there needs to be a legal definition.
There's not a legal
Yeah,
definition.
no. All right. Well, the verdict, the jury is out on that one. We don't know. So yeah, just I guess err on the side of caution. Don't watch it. I don't know. All right.
Let me
So,
throw my new logo in real quick for the plug.
oh, okay, okay. So,
I'm proud of it.
yeah. So let's see. Visit. Oh shoot. Okay. Visit the Gravity Max website. I've got some fun things on the Gravity Max website. And last time when I tried to explain it, didn't I like not like I explained it very thoroughly last time,
Yeah,
and then
then
my
you did.
audio
You
was
did.
out. The
Yeah.
one time. Okay, so I guess I might as well explain that whole thing again. On the
While I
website,
search for my logo.
on the website, I have links to all of my social media, okay? And I have my contact email, so if you want to contact Gravity Max for business inquiries, uh, then it's the email account is gravitymaxcontact@gmail.com. So yeah, business inquiries or just, compliments, I guess. Fan appreciation. I guess yeah. I guess those are business inquiries and compliment slash critique, I guess. That's what you can use that for. Um, I also have a public comments section that I jury rigged on the second page, and that involves a Google form and a Google spreadsheet. So very high tech. Uh, then on the last page, this is the best page in my opinion, is the page about my books. Um, and we've got a truly dead rock, and we have a little like synopsis, and then the like first few pages of the story, and a link to the Amazon. Then we also have a countdown timer for A Bottled Up Flame, which is my second book, and it is the sequel to A Truly Dead Rock, and I am working on the third draft right now. So, yeah, so visit the website. It's pretty cool stuff. Also, follow Gravity Max on social media, Facebook, Instagram, and Twitter. Links in the description below. We post, sometimes I post daily. Probably this week, I'm not going to post much because I don't have
It's understandable. It's understandable.
yeah, ain't nobody
It's
got.
understandable.
But after that, I try to do it daily, but it's kind of inconsistent. But if you want inconsistent updates and memes, then follow these social medias.
They actually are all consistent. You just travel near black holes.
Yeah,
So that,
exactly. From my perspective, it's a constant rate. Yeah.
yeah.
So links to that in the description. Also, oh yes, wait, I gotta exit the presentation and then bam, look at that. 128 seconds on YouTube. So what's that?
Look
So
at that logo.
visit Sebastian's social media and his YouTube. We've got Instagram at Karl Marxman. And
Oh, no, I changed it. Oh, right. I changed it.
what happened to the Instagram logo right there? I am
Hmm?
unsettled.
Oh, I
I
don't
am
even know.
unsettled. What happened to the dot?
I don't know. But I'm actually 128 seconds now.
Oh, okay. Well,
Instagram. I just changed it if you want it.
will the link in the description still work, or is that link like dead now because you changed
It
it?
should. I could check.
Okay, so
I have the stream on this monitor over here.
yeah. Well, if you want to
I should
find
probably have.
Sebastian's social media, just go to my Instagram and then he
Oh, yeah, no, the
likes
link
most of the
doesn't work.
posts. Okay, we'll fix it then. He likes most of the posts, so just he's his if you see 128 seconds within the likes on the Gravity Max social media. Well, I'm pretty sure anyone who's watching is probably already either subscribed or is like, I don't care at all. Why do you keep doing this every week? Um, so then, yeah, also visit 128 Seconds on YouTube for educational videos that are 128 seconds long. Very convenient, like you're about to walk into, I don't know, an exam. Just pop
Yeah.
open 128 seconds. It's like a little emergency.
Do you want me to
Like,
read off my channel description? Because I basically just pitched my channel.
oh sure, yeah, let's hear it.
Or, yeah, the about. Ever wanted something explained quickly? As the news speeds up, you need to be informed faster. Welcome to 128 Seconds, where you get simple summaries of complex topics. Videos every Wednesday.
Nice.
There you go.
That was good.
And I've officially passed 300 views on my channel.
Nice.
You
I
see, you
really
thought
like
I was
the
gonna say subscribers there, but
I like the aspect, the news aspect. Anyways, also we have a new thing in the plugs that you may not have noticed before, and that is 128 seconds Twitter. I think you started that this week, right? Yeah, so I find it pretty humorous.
I had to delete a. I'll tell you what it said. I
Oh,
can't say it on stream,
oh
but I had to
no.
delete a post.
Really? What? I'm really curious as to what it said. Here, wait, can you text it to me?
Yeah, I can.
Okay.
But we should get
So,
to move on with
yeah,
the
yeah, yeah,
actual.
yeah, yeah. I'll just. Okay, so yeah, go to 128 seconds Twitter for funny things. Links in the description. Yeah, they're pretty funny. They're like that one account. Like I've seen, like it's funny. It's like it's intentional typos and stuff like that. Um,
Yep.
so yeah, all right, all right. So then we got a Truly Dead Rock available on Amazon. You guys should buy it. Oh, you guys should buy it. You might enjoy it. If you guys like sci-fi and you like this channel, then hey, why not buy the book? Give us some support. Why? Anyways,
I was in a weird mood.
you were in a weird mood. Okay. Um, did they like remove it from Twitter? Did the Twitter bots or whatever like?
No, I just deleted it
Okay.
because I was like, what if colleges look at
Yeah. Okay.
what do you
So
mean by this post?
yeah. What do you mean by this? Okay. So yeah, buy the book, sci-fi book. It's fun. Got a sequel coming out in like 5.5 months. So yeah. All right. So then,
Relativity.
relativity.
We're not talking about your family. We're not talking about
Mm.
pop and Meemaw. We're talking about gravity. We're talking about the future light cone and the hypersurface of the present. We're talking about A. Einstein. We're talking about general relativity.
Yeah.
We're talking about Lorentz and clocks.
You're just reading through the.
Yeah,
Yeah.
but
Okay.
that's what we're talking about.
Yeah, that's what we're
Welcome.
talking about. So relativity. Relativity is like such an old concept, even before like Einstein put it into like stuff about light and time and space. I think it originated with Isaac Newton, who was like, if I'm moving at like 10 meters a second, that's indistinguishable from the world moving at 10
I
meters
bet some
a second,
Greek guy
and
actually
me
like
staying stationary.
postulated.
Oh, okay. Well, I remember that there's Newtonian relativity and then there's Einsteinian relativity. So Newton's relativity was just kind of like basic stuff like there is no experiment you can do in like where you're moving that you could tell that you're moving. So like if you're moving at 10 meters per second and you're in a closed box, it should be indistinguishable from just sitting stationary in that closed box.
And they are crediting Newton as the first
Oh,
guy to
okay.
do it.
Yeah.
I was just thinking maybe some Greek guy was
Oh,
eating his
some Greek
cheese
guy. Yeah.
and he was like, but what if
But
though?
what if, yeah,
You know,
almost right.
99% of what they said must have been absolute garbage, but they said
Mm,
so much that everyone thinks they're geniuses.
that's an
Yeah.
interesting idea. That's like it's like I've seen these theories where people say that like music from the past, like 60s, 70s, 80s music, isn't actually that much better than music from today. It's just like the only like we're looking at like 30 years of music so we can pick the best ones, whereas like today if you're like looking at all the new music, you're not like picking the best ones
That's
as
fair.
much. So I've heard that theory, but I don't know. Regardless, I like old music better. So there. So yeah, I don't care about that theory. No, I kind of care. It's interesting, but like either way, I'm still gonna listen to 60s, 70s, and 80s music. You can't stop. Um, so yeah, let's hop right into it. So history.
History.
We're gonna talk about the history of relativity. We didn't really go as far back as Newton. Like this video, I guess while it's called relativity, a more accurate title would be Einsteinian relativity because that's what we're focusing on. So yeah, all right. Albert Einstein, the man, the myth,
Chad.
the legend, right?
Chad.
So he was, like he's often accredited as like the smartest man in history. People always say that. Like when you insert like he's like used as an expression, like oh they're no Einstein or something like that. Like you always hear that. So very influential person, and yeah, it's interesting. So when he came up with his theory of relativity, he was working in a patent office in Bern, Switzerland. And that's him on the right in the patent office. Look at all those patents, I presume, right? So, um, yeah, so that's where he worked, and that's interesting. Like science was only his hobby. Not really. He was a scientist, but like it's interesting that he needed like this day job, pretty much. Like like he was a stand-up comic trying to break into the, you know what I mean? Like, it's interesting that when he came up with relativity, it wasn't like that was all he was doing. He was also like working at a patent office. So,
Yeah.
all right. I think that's yeah. Anything else you gotta say?
Little known fact about Albert Einstein. His middle name is. He does not have a middle name.
Wow. Okay. Thank you for that. I didn't know that he didn't have a middle name. Okay. Anyways, so special relativity is this was from Einstein's paper on the electrodynamics of moving bodies, and it was published on June 30th, 1905. So over 100 years ago, 115 years ago. It's quite a bit. We're approaching the 115th anniversary of this paper. Um, but yeah, it's very interesting. So this is where he first proposed special relativity, and you might hear of like special relativity and general relativity, and you might be like, "What's the deal? What's the deal? How are we running out of time? Oh my God.
What's the deal with? Oh
What's the
no!
deal with not being able to glitch out Zoom?" Okay,
Yeah.
so I guess we'll have to deal with that in a little bit. Um, anyways, so special relativity is like a very specific form of relativity. So that's why the like name special comes in, because it's like it's a special circumstance that this applies to. It's kind of like, how do I put it? So Einstein, he like had this idea, right? But before he could have general relativity, which like describes everything, he's like, okay, it'll be difficult to describe everything. So let's just describe one type of situation first, and then like using that we can expand and talk about everything else. So that's like an interesting way to solve a problem. Like when you're doing a like very complicated math problem or logic problem or something like that, um, the best way to do it is to like simplify it as much as you can, like until you have a form that you can do. So like if you're doing a problem that works with a sphere, right? Simplify it to a circle and then see if you can figure it out easily with the circle. And once you've done that, then you can bring it back into the third dimension. So that's kind of what was going on here. So special relativity only applies to inertial reference frames. And an inertial reference frame is kind of like what we were talking about in Newtonian relativity. It's any reference frame that is moving at a constant speed. So no acceleration, no gravity. So like, not even just me sitting here on Earth. Like it would just have to be moving in a straight line through space at a constant speed. So that's kind of what special relativity applied to. But it was like very important even then because this like it would describe time dilation as a result of speed. That's kind of what this talked about. So this basically said like as you approach light speed, right, what happens is your sense of time slows down, your mass increases, uh, length contracts in the direction that you're moving, and the result of all that is that since your mass is increasing, it takes more and more energy to accelerate every extra meter per second, right? So that by the time that you're approaching light speed, it would take all the energy in the universe. It would take an infinite amount of energy to actually propel you to light speed. So you can never get to light speed. That's like why things can't move at light speed, other than light, because light has no mass, and there are a few other particles that don't have mass either. And massless particles can move at light speed because their mass, multiply zero by infinity, it's still zero, right? I don't know. It's actually like some weird. I think it's an undefined situation.
About 8.
Yeah, it's kind of like a zero divided by zero. It's
It's about 8.
about eight. But yeah, basically photons, they are massless particles, so they're able to move at light speed without needing an infinite amount of energy to do so. So yeah. Then what else? So yeah, this is where we get time dilation from the initial perspective, the speed perspective of time dilation. And this is where we get like you can't go faster than light. So this is interesting because Einstein, he agreed with Newton that if you are going 10 meters per second, there's no experiments that you can do to prove that you are moving at 10 meters per second. That, same thing with like 0 meters per second, right? So, that's kind of what he was working on. But then he thought, right, well, what if you are moving at, say, 50% of light speed in one direction and someone shines light in that direction? Will you see light moving at 50% speed relative to you? Because if you think about it, if you are moving, say light moved at 10 meters per second, right? You're moving at 5 meters per second, light comes past you at 10 meters per second. From your perspective, it would only be moving at 5 meters per second. It's like how if you're on the highway and all the cars around you are moving at the same speed, they kind of look like they're stopped, even though you're all moving at 60, 70 miles per hour. So that's kind of what he was saying, like, why don't we see this happen? Because we don't see this happen with light. You could be moving 99% of light speed, and light will still look like it's going at 100% speed from your perspective. So he was like kind of questioning this, like, why does this happen? This wouldn't happen with any physical object. You could throw a baseball and you're running along it, and that would have slow its relative speed. So special relativity, as opposed to Newtonian relativity, is basically saying that for some reason, light speed is like this constant that everything else must adapt to. So this is kind of where the logical process begins. This is where we get time dilation from. Is if you are moving at 50% light speed and light comes by at 100% speed, and you should be seeing it at 50% speed, but you're seeing it move at 100% speed, then the question is, how is that possible? So it's possible by slowing your sense of time. So if you are physically, like, if you would point at a clock in your spaceship, and that would be like, ticking by slower, but remember, from your own perspective, you wouldn't see it ticking by slower. Like everything seems normal. That's like why it's like relativity. Everything seems normal for like all intents and purposes. You could be stopped, right? But like it could be not moving at all. Uh, but since your sense of time is slower, light appears to move faster. And then it's the same thing with length contraction. If your measure of distances is shorter, then it'll take more units to count the same distance. So it'll seem like things are moving faster. So that's where we get all of these different aspects of like relativity from, all these weird like relativistic effects. So yeah, this is a very important.
Yeah. So yeah, a lot of people and I'm just gonna say this quickly before it times out,
Oh
but a
yeah.
lot of
Oh shoot.
people know. Yeah, a lot of people know that Einstein's like the smartest guy, or like in their mind, if you ask someone 9 times out of 10 who's the smartest guy, they're gonna say Albert Einstein.
Yeah.
But not a lot of people know why it is. Like they can be like, oh, E equals mc squared. And that's part of it, but it's the fact that he was able to encapsulate what relativity is, because before him it was like Newton, who kind of thought of it. He didn't really have much to it. He just had a general idea. And Newton was a smart guy, don't get me wrong.
Yeah.
But all he had was an idea. And it was Einstein who, how many uh, years later, was able to make all these theories on it and really comprehend it in his mind.
Yeah. Well, it's an interesting question. Actually, I'll bring this up when we get back. So it's just
Show the meme before we go out.
which.
On the next slide.
Oh no. I'll wait. I'll wait.
We're not? Okay, we're waiting.
I'll wait. I gotta.
We wait.
We waiting. I gotta. I have a few more comments about special relativity. Okay. So yeah.
All right.
In a second. Meeting. Okay. Hello. Yes. Yeah. Okay. All right. So now participants. Right. Let me just not expose our person. Email accounts. Oh, wrong one. There we go. Okay. All right. Gmail. Okay. Back to relativity. All right. So, okay. Here we go. That's session. All right.
There we go.
Yeah. All right. Okay. Let's make sure there's no echo. Yeah, everything sounds good. Okay. Um. Yeah. So an interesting question is the question of like time period, right? So it's kind of like how people always say that someone's like a product of their time or whatever, like in reference to usually when someone says that, it's to like excuse bad things that someone did
Yeah.
because they're like, oh, it was okay at the time. Um, but what I mean here is that if Newton was like born the same year as Einstein, right? Um, would he have come up with like special relativity and stuff like that? Like Da Vinci, um, because as humanity, we kind of like build off of our past generations. So it's kind of like interesting. It's like how can you compare, one generation to another generation when it's like they weren't starting with the same set of knowledge, you know? Um, so it's interesting how you would figure out who exactly is the smartest person in history. It could just be like a random person. Um, but yeah, that's an interesting question. But yeah, that's it. Yeah, that's special relativity. All right. Let's go to the meme. I'm kind of forgetting what meme this is. Is this? Let's just see it. Oh yes, okay. When was Las Vegas discovered? May 15th, 1905. Society in 1904. So, of course, I don't mean discovered, I mean founded, but that's kind of the format of the meme is discovered. But also, Las Vegas is just older than special relativity, which I don't know. I think that's kind of how humanity got set down the wrong path, don't you think? It's interesting. What if just a month and a half later, if Las Vegas was just founded like a couple months later, then maybe we would be so much further ahead. If special relativity preceded Las Vegas.
Mm.
What do you think on that? It's an interesting butterfly effect question.
Yeah, well, this is obviously the Vegas relativity continuum.
Hmm.
And I don't know. I think it might be more connected than we know. Because what if Einstein went to Las Vegas? Right? He took a little hiatus
I'm pretty
from
sure
his
he was just in Switzerland.
took a hiatus from his job in Switzerland.
Hmm.
You follow me? And he goes over. I don't think they had planes, but he walked across the ocean
He
because
walked
he's
across the ocean.
that smart.
Okay.
So he walks across the ocean
All
and
right. I'm looking
he
this up.
comes over to Las Vegas.
Okay.
And as he's partying and he's lying there, he's like, I got an idea.
All right.
And
Well,
that's
here's what I think. I don't think Einstein had even been in America until the 30s. When he left
officially,
officially. Okay.
like
Um,
officially, I'm not allowed in the state of New Jersey. Does
okay.
that stop me? No.
No. Well, why would you want to go to New Jersey? If New Jersey banned me, I'd be like,
Fair point.
thank you.
Fair point.
I'm just kidding. Don't be offended, New Jersey. Yeah, Einstein left Europe in 1933. He went to America because Germany was increasingly becoming a fascist regime, right? So, yeah, trying not to get demonetized. I don't care about money. We don't earn money here on the Gravity Max live stream. Anyways, all right. So, general relativity. Hats off to you, sir. Um, this is just a joke. A bit of a joke,
She
but
fits into the quantum mechanic universe,
yeah,
obviously.
yeah, it's an addition to the quantum mechanic saga. Remember, there's the quantum mechanic and his family, then there's also Silas. But general relativity is actually the quantum mechanic's father, according
Wow, I
to
didn't think you were
Gravity
gonna drop
Max.
that knowledge on him.
Yeah, yeah. So they are actually father and son. But the thing is, they don't see eye to eye. You know, quantum mechanics, relativity, they never seem to like get along. So, um, yeah, so they've got a bit of beef. Um, and that's why we don't have a grand unified theory. That's what's going on.
Yeah, it's that familial dispute.
Yeah, yeah, it's just a familial dispute between general relativity and the quantum mechanic. Wordplay. Anyways, so general relativity applies to situations where acceleration or gravity, but they're kind of the same thing in this perspective, right? So it's where acceleration is involved. So this was like 10-ish years later. So this took quite a bit of development. Um, but
And this is the one you hear
yeah,
more often about
yeah,
as well. You hear general relativity much more often than special relativity
mhm.
because we like black holes and other things. And also, it probably, I don't know if it has more practical applications, but
Definitely. Yeah, it applies to so many more situations. I mean, that was the whole like shtick, I guess, with special relativity was that it only applies to inertial reference frames. And inertial reference frames are, I would say, they are impossible, right? They're a theoretical concept, but like you could never have a thing that's perfectly moving in one direction without any acceleration, you know? The universe is filled with things, and because of the inverse square law, gravity may like become very like minute, but it's always there. So there's always acceleration. So there is so special relativity is like a mathematical kind of concept. It's like it's kind of like you're opening a blank simulator, like a blank sandbox. If you know the game Universe Sandbox, right? It's like you're opening up a blank sheet of space-time and just placing individual objects in it and, accelerating them, putting them on their paths, right? And just no gravity, nothing, which isn't how the universe actually is. The universe is filled with stuff. So, um, general relativity is the only one that actually applies to the entire universe. So it incorporates the concepts of special relativity with, the inertial reference frames and how velocity affects time and stuff like that. But it also introduces acceleration as something that can influence time. So mass dilation and length contraction are like I think they're uniquely um, dealing with inertial reference frames. But time dilation can actually come from two sources, and that is speed or gravitation. And also, I keep saying speed. Just assume I'm like saying velocity. Okay, I'm sorry, semantics people if you are unhappy that I'm saying speed instead of velocity. But when it comes to relativity, speed and velocity are interchangeable, actually. Um, so here's the difference if you don't know. Velocity has a sign. So if you are moving this way, that's positive 1 meters per second. Moving this way is negative 1 meters per second. But speed is just like the absolute value of that. So 1 meter per second, 1 meter per second. Um, but in relativity, because of something that I'll show you a little bit later, the Lorentz factor, velocity is squared in all of the equations. And you know what happens when you square something, it's always positive. The square of an absolute value is the same as the square of just the number.
A
So
negative number.
I will continue to interchangeably use speed and velocity for this video, and I do not care how
He's
mad
a
you get
madman.
about it,
He's
okay?
on the loose.
I am a madman. I am a menace,
The
okay?
SWAT is about to raid you, bro.
Oh no, I'm gonna get, oh gosh. Yeah. There you go, on the
Yeah, I
ground.
hope so.
On the ground, are you talking about velocity or speed? Which one? Yeah, I'm talking about both, okay? It doesn't matter. In this instance, it doesn't matter, okay? So don't get
So
your, I don't know, don't get offended.
yeah, with general relativity,
Yeah.
um, I read, and I believe you read it too, The Elegant Universe by
Yep.
Brian Greene.
Yep.
Um, a large part of that was quantum mechanics, because he talked about string theory, and string theory is supposed to be the bridge between quantum mechanics and general relativity.
Grand
But
unified theory.
yeah, the grand unifying theory of
Yeah.
physics. But he didn't talk about general relativity too much in that book. He talked way more about quantum mechanics and percentages of like trying to predict where an electron is, position
Yeah.
versus momentum. That's the Heisenberg uncertainty
Yeah.
principle, which I made unlisted on my channel because it was terrible. But
Yeah. Heisenberg.
the general relativity is usually seen as the physics of the very big, because when you're talking about black holes or when you're talking about planets or you're doing the Newtonian two body problem, stuff like that, that's usually done with like planets or galaxies, even, and stuff that's so incredibly dense has a ton of gravity. And general relativity seeks to understand that or
Mhm.
explain that. Meanwhile, quantum mechanics is more like, why do particles be doing that though on the
Why do
small
they do
scale? Because once you shrink down to a small enough scale, like Ant-Man going into the quantum zone,
that?
um, once you shrink down to that scale, particles move in seemingly random positions. And it's not like you see them go like this, it's like they teleport over here,
Yeah.
you know?
Quantum.
Um, it's probably not random because it's probably something we just don't understand yet, because there's a lot about quantum mechanics we don't understand yet.
Yeah.
There
Yeah.
could be some force that we're not aware of, but for the moment, it's pretty random, and it doesn't really go with general relativity because of gravity, and by extension, because gravity doesn't go with the two, time also doesn't go with the two. Because
Yeah.
general relativity states that if you just vibe near a black hole for like 25 years, it only like 3 days could have passed on
Yeah.
Earth. If
Or well, 3 days passed for you, but then 25.
yeah, yeah, no, yes, that's what I mean. Sorry. But in quantum mechanics, time is seen as an absolute constant. An absolute constant.
Yeah.
And string theory is like, why not both? And it's crazy. But this isn't
Yeah.
about string theory, though. We could
Yeah.
do it.
Yeah.
We could do
That'll be that. It'll be like an arc. They'll make each other like, I don't know, little
Yeah,
lanyards.
little friendship bracelets
Yeah,
on
exactly.
strings.
And
They're
that's
like,
how they. That's yeah. And then yeah, exactly. Um, but yeah, it's really interesting. Relativity, all of the effects. Shoot, I was gonna say something, but I'm kind of forgetting what I was
ha
gonna say.
ha.
Yeah, I am a fool. Anyways, let's see. So, oh yeah, well, so I guess I should talk about acceleration a little bit. So, the thing with inertial reference frames, right? That's like a bit of a problem with special relativity, and it actually creates some paradoxes. But uh, if you only like if only special relativity existed, these paradoxes that we're going to talk about later would be unresolved, I think. But with general relativity actually resolves all of these paradoxes. So they're supposed paradoxes because they aren't paradoxes anymore. Um, and this is basically the idea that uh, two inertial reference frames, like there is no absolute reference frame, right? So if you have a system with one body that is stationary and another that is moving away at 10 meters a second, that is indistinguishable from a system where, the one that's moving is actually stationary and the other one is moving away at 10 meters per second. The only reason that we would say my hand moved is that we are all rooted to the earth and like the rest of the universe. But, if we were, I don't know, a colony of bacteria living like on my hand. And not that my hands that dirt, it's just that like, there's bacteria everywhere, right? I wash my hands, okay?
He doesn't.
We were if we were tiny people on my hand, okay? If we were tiny people on my hand, we would be like, wow, this huge like room is moving. Not that we're moving, you know? It's kind of like the geocentric versus heliocentric models of the universe, it's where they used to think that everything spun around the earth because the earth was spinning. And we were on it, so we really couldn't tell the difference until we thoroughly investigated. And once we did, we figured out that, like, oh, it's actually the earth is moving around everything else. But with just a cursory glance, it's hard to tell. But acceleration provides you uh, that context because if two objects like started stationary and then one began accelerating away and eventually started moving away at 10 meters a second, then you know that this is the object that's moving and this is the object that's stationary. Because while it's true that if you are in an inertial reference frame and you are moving at whatever speed, there is no test you can do to determine that you are moving. If you are accelerating, you can actually do a test that figures out that you're accelerating. And you probably like feel that if you've ever, been on a train or a car or a plane or something. Um, your plane, is moving at many hundreds of miles per hour, right? And you don't even notice. You're fine. It just feels like you're sitting in a cramped seat, right? But when your plane like comes in for a landing or it starts taking off, that's when you feel the acceleration and you feel pushed back in your seat. So if you were to throw a ball up in the air in the middle of the flight, it would come right back down in your hand. But if you were to throw a ball in the air as you started accelerating, it would end up moving like backwards, moving behind you because it is not rooted to anything that is accelerating. So, and it would be moving on an inertial path, which would be a constant speed. So it wouldn't be moving as fast as the plane is moving. That's pretty much uh, why like acceleration is a fundamental thing. That's kind of what general relativity states, is that acceleration or gravity um, is actually like meaningful, whereas velocity slash speed isn't meaningful because it's just about perspective. Acceleration isn't about perspective. There is no way that someone that's just sitting in place can say, "Oh, I'm just accelerating right now." There's nothing. You can't say that. That doesn't work. Um, so yeah, that's kind of what happens. So gravity and acceleration both cause time dilation, but Earth gravity and earthly accelerations don't. So don't expect to like hop in your Tesla and go from 0 to 60 and in like a second, right? Like I don't know, they're crazy fast, like very good pickup. But don't expect to do that and then come back 30 years in the future, right? That isn't how it works. You'd have to be
You
accelerating a
have to go
crazy
88 miles per hour.
88 miles per, yeah. No, the problem would be the acceleration would be too much for a human. It would likely kill you. So, and not likely. It would actually definitely kill you. So yeah. But if you were to accelerate a computer that was resistant to acceleration, then you could probably detect something like that. And if you were to orbit around a black hole, right? Even though there's so much gravity, since you would be in orbit, which is a free fall, uh, you would be fine. Kind of. There are other things that would make you not fine, but the acceleration wouldn't be one of them. So yeah, that's kind of the situation.
I don't
Um,
know if we've like talked about it before, but just because you said orbit is a free fall, I
Yeah.
think we should
Oh,
explain it. Um, Whenever you're going in space, you're going in a straight line, but it's gravity that curves that line. So
yeah,
when you're orbiting something, you're actually going completely straight, or you're like falling forever, you know.
yeah,
But you're going, it's curved because of gravity, because gravity curves time and space, which ties into what we're talking about
yeah.
here.
That's a lot of what Einstein did as well. Yeah.
Yeah.
Um,
I don't know
yeah,
if we've ever said that like directly, you
yeah,
know,
yeah,
but
yeah. So,
it's an interesting point, you know, and it's
yeah, it's
kind of what
interesting.
got me into physics in the first place.
Yeah,
Because when I heard someone say that gravity bends space and time, and when something's orbiting something, it's going straight, I was like,
whack, right? Yeah. Um,
"Nani?"
yeah, exactly. So, yeah, it's a straight line, and when you accelerate, that's when you move off of the straight line. So, acceleration is like, I don't know, it's this crazy entity. It's much more than you think it is. Um, so yeah, I think that's but yeah, acceleration causes time dilation, and I think that's it. I think that's general relativity.
Yeah,
All right. So
we had
mathematics.
the mathematics
Yeah, mathematics.
brought to you by Nigel.
No, do not impugn Nigel's name, okay? I got it on random name generator. He's supposed to be an American.
Well, yeah, yeah,
Okay.
failed. The name
Oh,
generator failed.
I'm just gonna I'm gonna name my kid Nigel just to piss you off.
Just to
Be like,
spite
look,
me.
he's American. Yeah, yeah, that's what I'm gonna do. Okay. Um, we're just referencing a pre-stream conversation. Anyways, we're going to talk about some mathematics. We're going to talk about the mathematics involved in relativity. All right, so
Lorentz
begin.
Factor. I love this table that
I
you got
know,
on. It's
it's
great.
wonderful. Yeah, we begin with the Lorentz factor or the Lorentz transformation. There are different words for it. Um, but basically, it's this like, it's kind of the factor that things are affected by like relativity. So it's time dilation, mass dilation, and length contraction. It's all this factor. So what this factor means, square root of 1 minus v squared over c squared is it's in whatever unit you want. That's the use of the over c squared. But if you use units of, fractions of light speed, then you can just, you know, what's it called? You can generalize it to the one on the left, 1 over 1 minus v squared, but that's only for one unit. So basically, you square your velocity, say velocity of 100 kilometers per second, okay? So you square that, and then you divide it by the speed of light squared. And since we're talking about kilometers per second, that would be 300,000 kilometers per second. So that gives you like 1/9 in this instance, right? So then 1 minus 1/9, that gives you 8/9. And then the square root of that gives you, I don't know, I don't want to, fine. Have a calculator, so might as well, right? Okay, so yeah, so 8 divided by 9, and then let's get rid of frame lock. Okay, so then square root is about 9.94, and then 1 over that is, 1.06. So, yeah, okay, so basically what that means is that if you are moving at
Checks out.
100,000, yeah, if you are moving at 100,000 kilometers per second, and you do that for 1 year, then back on Earth, 1.06 years will pass. So that's the time dilation factor. It's a simple calculation, it's a simple equation. Like we can do the same thing for 200,000 kilometers per second. So that would be roughly 2/3 the speed of light. So 2 divided, or well, that would become 4/9, right? And then 1 minus 4/9, 5/9. And then, square root that. and you get about 74%. So then you 1 over x. So if you were to travel for 1 year at 2/3 the speed of light, it would be about like 16 months back at home. So this is interesting because if you were to graph this, it stays flat for a long time and then it goes crazy, it spikes. Um, because yeah, even at 2/3 the speed of light, you might be thinking that's not very time travel-y. What's up with that? An extra 4 months pass. Oh no, I'm missing
Yeah,
out on
skip
important.
quarantine.
Yeah, skip quarantine exactly. Yeah, quarantine on a spaceship. Time dilation, 1 day passes, 4 months pass on Earth. So yeah, if you want to get crazy time dilation like that, you have to do something that's like, say, 99% the speed of light, right? So 99% the speed of light, then you square that, and then -1, blah, 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 and then square root, and then 1 over x. So 99% the speed of light gives you a Lorentz factor of about 7, so 7.08. So if you were to travel at 99% the speed of light for 1 year, you would come back 7 years later. Now that's some pristine time dilation. That is what I'm talking about. Spend 1 day in time dilation and a week passes, that's great. But yeah, things get crazier as you move closer to the speed of light. So let's say 99.99% the speed of light. Um, so yeah, then you square that, -1, 1 minus blah, 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 and this is just the standard equation. Like you can do this, pick any fraction of the speed of light. Pick the speed that you drive on the highway. You're gonna pretty much get 1.00000 like whatever, right? Because that's the thing. Time dilation really doesn't take effect until you start moving at very quick speeds. So yeah.
So
Um,
when or if we get FTL technology,
mhm.
how would that affect the dilation? Would it just heighten it more?
Well, here's the thing with FTL. FTL breaks relativity. So relativity like doesn't work anymore. Um, oh yeah. So with 99.99% the speed of light, the factor is 70. So you leave for a year and you come back and everyone is dead because everyone you knew was dead. So that's your you know Lorentz factor. But yeah, this only I'll get to your comment in a moment, but so the Lorentz factor only, like with time dilation, is only a method to travel into the future.
Futurology.
Future. Oh, we do we have
Futurology alert.
we have a comment? Oh shoot.
Rings bell.
Okay, okay. But yeah, so time dilation is only a method to travel into the future. You can't travel into the past. But yeah, what you were saying with FTL technology. Let's see what futurology says. Futurology says, dude, I love that equation. Used it for my time travel video a while back. Yeah, exactly. So you're able to travel into the future,
I
but
love you, futurology.
yeah, but this equation will never output a negative value, which means that, the only way to get a negative number when multiplying it by a positive number, that's it, you would need a negative Lorentz factor. And because it is 1 over a square root, square roots are always positive, or I guess imaginary. So that's actually what happens. If you move faster than light, you want to see what happens? All right. So say that you move 2 times light speed, okay? You go twice as fast as the speed of light. And of course, this would be impossible, but say somehow you did it, right? Um,
Warp 2.
yeah, with classical relativity, or not like with Einsteinian relativity, which, you know, Einsteinian relativity like doesn't even allow for this. And this is part of the reason why. So say you put 2 times the speed of light into your Lorentz factor equation, okay? So you get 2, then you square it, and then, so that's 4. 1 minus 4 is -3. Square root of -3. My calculator says error. So yeah, that's the problem. But if you wanted to just press on anyways, the answer would be the square root of 3 times I, and then 1 over the square root of 3. times I, so it would be imaginary. So I guess you would just kind of like fall into the quantum realm. That's kind of what would happen. You would glitch out. So yeah, that's kind of why you can't go faster than light. But yeah, if we're talking about warp drives and stuff like that, the way that a warp drive works is that it moves a piece of space faster than light. So the way that they reconcile this with relativity is that you are actually stationary compared to space. You are like, there would be no time dilation, no acceleration. That's the key part. You would not feel yourself accelerating at all. And that's very important because oftentimes in movies, they'll go from like stationary to like warp 37 in like an instant, which would dismantle everything. You would get a fine dust, not even a dust. You would get a fine quark gluon plasma. It would just be so like, it would be more catastrophic than any like weapon known to man, right? Um, so yeah, you see your time limit again. But yeah, so you're moving a piece of space and you are sitting stationary in it, so there would be no time dilation, and theoretically it wouldn't violate relativity because space is allowed to move at whatever speed. Because if you think about the expanding universe, right? The very edges of the universe are like moving away from us faster than light speed. So it's like, how is that possible? Well, it's possible because it's space. So a piece of space is allowed to do that. I guess that's kind of how it is. So yeah, that's the Lorentz factor. The Lorentz factor also does mass dilation, except instead of multiplying by the factor, you have to divide by the factor. So that pretty much means just ignore the 1 over, um, or something like that. So let me just show you that. So say you're going 0.99999, right? And so that was like a Lorentz factor of 70, right? So if you have your mass at rest is 1 kilogram, then when you're moving at 99.99% the speed of light, it becomes 70. 99.9999, and it would be 700. So it keeps going like this, 7,000. And you can never actually get to the speed of light because your mass will approach infinity. So that's that.
There you go.
And then the final one is length contraction. And what happens with length contraction is just like you would kind of like look like a pancake going through space at 99% the speed of light. Your factor
We
would be
slide it.
7. So yeah, say 99% the speed of light with Lorentz factor of 7, you have a spaceship that is 1 kilometer long. It would be 1/7 of a kilometer long at that speed from an outside observer, of course, because again, from your own perspective, everything is normal and everyone else would look contracted. So you would float by the Earth and it would look like not the Earth. It would be interesting. Um, so yeah, that's Lorentz factors. All right. So yeah, next slide. Lorentz transformation. So this has to do with the space-time diagram, and the space-time diagram is a very useful tool, I guess you could say, because basically it will show kind of the world line. That's what they're called. It shows the world line of an object. So the y-axis is typically time, and the x-axis is typically space, and it's generalized.
Cursed. When
Yeah.
time isn't the x-axis.
Oh, yeah, you're right. That is cursed. Time is usually the yeah. So the x-axis is space, and it's generalized to one dimension. Like for the sake of the problem, it's like, do you really need 3 dimensions right now? Are you serious? So yeah, so the way that a world, also the way that it's scaled is that an object moving at light speed will be moving at a slope of 1, so 45-degree angle. So uh, it's kind of like the y-axis could have years, and then the x-axis would be light years. That's kind of how it would work, or seconds and light seconds. So that's the way it's measured, which means that what we think of as a small amount of time, like a second, would correspond to a very large amount of space, like hundreds of thousands of kilometers. So you got to think about that. Um, so yeah, so the way that the Lorentz transformation works is that the axes that are typically like, like this, they end up warping and becoming like off to the side and
Yeah.
get all skewed. You kind of see that in this picture. And the reason that happens is, to fit like the object moving through space. So yeah, it's actually very interesting because you see that I'm trying to interpret this right here. Uh, Basically, it's like 3 units of time pass, but then for the object, it's more than that or less than that because it's like moving at lights or not light speed, but relativistic speeds. So yeah, what this kind of describes is you would end up with a hyperbola, and that hyperbola represents 1 second depending, or 1 unit of time depending on speed. So if you are to move straight up, which means stationary because you're only moving through time and not through space, that is where you cross the 1 second line. Let's just say 1 second. You cross the 1 second line the soonest. But if you are moving very close to light speed, right, then you're like way up in the space-time diagram, and it could be years and years, millions or billions of seconds could pass before you reach that first second on the hyperbola. And that's just how the Lorentz factor like becomes graphical. And
We have some chat from
oh yeah,
futurology. And yeah, he's talking about the bots. I knew there were bots, so I don't talk to them, but I didn't know you could get hacked from them.
oh, if you weren't already aware, do not respond to any of the Let's Be Friends comments. If you interact with them, your account could be hacked. How
I knew there
so?
were bots, but whack.
How do they hack your account? I would
I
like
don't know.
that.
Change your password.
I
He
know, but
said.
like from like just seeing a comment,
I
like
don't
how do
know.
they do that? Just by like how does like that seems like a YouTube Matrix thing. Well, that's rough. I'll make sure not to do any of that.
Thanks, futurology.
Yeah, thank you. That's troubling. I think it actually hack you. Interesting.
Am I talking to Max right now? Or simply a hacker that looks like Max?
Well, I'm changing my password today because I haven't changed it in a while, and now I'm kind of paranoid. So yeah, I have a good, I have a password that I like. It's a phrase that I like. So, um, yeah. Oh yeah, here's a tip.
Just
Always,
subscribe to Gravity
yeah,
Max.
no, no, no. Always, here's a tip, right? Never have a password, have a passphrase. So think of a sentence like, I don't know, this isn't mine, but like a lyric from a song. So like you could say like took the Chevy to the levee, but the levee was dry, right? If that's just the song that's in my head right now, okay? But like if
He has
that's
been
just,
obsessed with American
yeah,
Pie
I like that
for
song right now.
years.
For like a week, okay?
A week, same thing.
Yeah, that's years in max time.
Yeah, you just we move indifferently with
Yeah,
time.
yeah, all right. No, I've just but yeah, say you make your password a lyric from a song, like something that you'll remember. That's and it's so long that like traditional password, which is the brute force attempt where they just like AAA, AAB, AAC, AAD, like they try all that. So that's a good way to protect your password. Um, but yeah. Anyways, let's just I guess
Yeah,
well we should probably restart the Zoom meeting
yeah.
before we continue.
And we will pick
Um,
up with
yeah,
another of Einstein's flexes.
another top 10 flexes. Okay. All right, all right. So let's. Yeah, I'll end meeting for all. Okay. All right. Okie dokie. So let's just turn off this one. Okay. New meeting. And join computer audio. Invite. Email. Gmail. Relativity. Okay, let's turn this back on. And there we go. Okay. All right. Okay. And we're back. All right. Let's see. Let's see. Okay. All right. We all good?
We good.
Yeah. All right. All right. All looks good. Okay. So let's continue. Energy mass equivalence. So this is a little meme right here. We got you versus the guy she tells you not to worry about. And the origin of this is that um, the iconic equation E equals mc squared originally was m equals L over c squared. Ew. That was the way Einstein originally wrote it. L stood for energy for some reason, and m stood for mass, c for the speed of light. Um, and yeah, so he changed it, thankfully. Multiplied both sides by c squared and changed L to E. So then you got E equals mc squared. And yeah, so basically the energy mass equivalence is an interesting one, and it kind of carries it. You see it a little bit in relativity, and here's like one instance I'm thinking of right now. So the mass dilation. Uh, the way that mass dilation works is because of energy mass equivalence. So as an object approaches the speed of light, it increasingly gains kinetic energy. So the object is not only holding its mass, but it's also holding the mass of all this energy. It's like weird, but it's got all this kinetic energy inside of it, and that increases its mass so that it's inertial mass, so that like if you try to accelerate it, it'll be much harder to accelerate. So that's your E equals mc squared. Another place you see it is like, I mean, just nuclear, all the nuclear stuff, nuclear fission, fusion, that uses E equals mc squared because mass is becoming energy. And yeah, so my dog's barking.
And he going crazy.
Yeah, do you have any comments? I'm gonna speak up. I'm gonna speak loudly. Shut up.
I think Annie wants to weigh in on the energy mass equivalence. She's like,
Yeah, Annie, what do you have to say
as a
about
fraud.
Oh,
If you're
you don't
Hmm?
Oh, that's interesting. That's an interesting proposal. Huh.
What?
Never thought
Einstein's
about it
a
that way
fraud?
before. Never thought about it that way before. That was so enlightening.
Yeah.
Anyways, what else do you have on the energy mass equivalence? Anything? Comments?
Um, it's useful. I do a lot of chemistry. I be whipping up chemistry. That's
I'm
me.
Yeah.
So
I
you
mean,
gotta use, yeah.
yeah, it's one of the most famous equations of all time.
She agrees.
Oh, really? Wow, that's so interesting. Uh, um, let's see. How much is OBS picking this up every time she barks? Okay, a little bit. Do you hear it?
Yeah, I hear it.
You hear it. Oh my God, I don't know what my dog is barking at. There might be like another dog or something. This is like constant. It's like a tempo. Okay. Should we go to the next slide so
Yeah,
we
let's
have
talk
more?
about light clocks.
Yeah, all right. Let's talk about light clocks as my dog
So
spazzes out.
some clocks are made with, whatever the hell clocks are made
Wait,
with
what
glass.
happened to the one on the left?
Yeah, the
What happened?
glass,
Why is it
the
all green though? What happened to it?
I don't know what
It's
did
weird.
happen to it.
I don't know what happened. Anyways, yeah,
But
sorry.
yeah, some clocks are made with all different materials. Maybe there's some iron in there. It's usually just plastic, though. There might
Well,
be
yeah, some are
some
made of
other.
like gold, redstone, and iron, right? I think that's the
Exactly.
Minecraft
Yeah.
crafting recipe
It's
for a clock.
four golds, one redstone, and one iron, I believe.
Yeah, okay.
But that is heavy. So what we did, we invented a light clock.
Oh boy. Okay. So a light clock is a theoretical thing. I don't think anyone has made one. Maybe they did, and I'm wrong. But
The
you're not just gonna buy one for your house, is what I'm saying. Um,
Oh, it's four gold, one redstone. There's no iron.
oh, okay. Four gold and one redstone. Um, but basically, what a light clock is that a photon is bounced back and forth between two perfect mirrors. And already, mirrors aren't perfect. You can't have a perfect mirror, so there's that. But just it's this is for the sake of argument. It's mathematics. Mathematics doesn't have to be real. Um, so when a light clock is stationary, say it is 1 light second long, just because that's easier to talk about than like microseconds, but a light second is massive. So just, pretend with me, right? Pretend that we're all giants, okay? So a photon bounces back and forth between, ooh, let's see if I can line it up with the zoom window. It bounces back and forth between the two mirrors once every second. Tick, 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 right? Um, so that would be like a perfect measurement of time because, light is a constant in the universe. So, yeah. But if you were to start moving, right, then the photon has to travel farther for each tick. So each tick takes a little bit longer um, because we do our, Pythagorean theorem right here, right? If these are both 1 light second tall, but now you're moving at half the speed of light, right? Then instead of moving 1 light second, your photon is now having to move the square root of 1 plus 1/4, so it's square root of 5/2 light seconds. That's how much it's traveling. I'll exact form is not fun for people. People don't like that, so um, I'll do it for you. Okay, there you go. So if you're moving at half the speed of light, it is now going 1.118 light seconds. Okay, and the problem with that is that, if you were to conduct this experiment, you would be like, hey, why, from your perspective, right? Uh, the light is bouncing just up and down, okay? But you would say, hey, why is it taking 1.18 seconds for light to move back and forth 1 light second? So that would violate relativity. So the result of that. This is kind of where we get time dilation from again. And that's like you're moving slower. So what like an outside observer sees as 1.18 seconds, you're like, yeah, that's just 1 second. So yeah, that's kind of the light clock is a more sophisticated form of saying a photon moves with you because it's bouncing between these two mirrors. So yeah, that's the light clock. I like it. I like the concept of a light clock. I want a light clock. That would be such a cool thing to have, right? Yeah. Anyways, all right. So yeah, let's go to the next slide. In practice, so we were talking about mathematics. We were talking about theoretical versions, right? So now, how does relativity like, in practice? Because we always talk about relativity and relativistic speeds like, yeah, this doesn't really, it's a very negligible effect in reality. But there are some instances where we actually have to think about relativity in just like normal life, human operations. So you might think that it's like, oh, you have to be near a really crazy black hole or you have to be moving at crazy speeds. But no, there's actually some like real life, modern day instances where we need to talk about relativity. So yeah, first we got this atomic clock experiment. And this was an experiment kind of meant to prove relativity, but like it had already like it was proposed as a theory, so this is kind of like gathering experimental evidence is sort of what's up. And the experiment was they got, a dozen, doesn't matter, n, they had an amount of atomic clocks, right? And they had half of them on the ground, and they put the other half of them on a supersonic jet, and just flew around for a bit, okay? And then they came back and they compared the atomic clocks. And since atomic clocks, um, I think they use cesium, right? Uh, and cesium, like it oscillates like millions of times per second, so very accurate. And they looked at these atomic clocks and they're like, hey, the ones that were on the jet have all reported
It
slightly less
is cesium.
times. It is cesium, nice.
Yeah. It's
Yeah,
I don't know what number you said, but 9.2 billion cycles per second.
I said millions, so I don't know, 9,200 millions. Um, anything larger than a million is millions. I could have said thousands, and technically I'd be correct. 9.2 million thousands. But that
There
sounds
are
so horrible to say.
dozens of atoms in the
Yeah,
universe.
there are dozens of atoms in the universe. How many dozens? Well, dozens just means more than one dozen. So yeah, technically the truth. R slash technically the truth. Um, but let's see. So yeah,
Now my dog's weighing in. He's like, "But
mhm.
that disturbs the
Oh yeah,
zeitgeist
that disturbs the psyche. Yeah, I hear your dog. Um,
of."
but yeah, so it's interesting. Yeah, the IA or not the IAU. It's another one. It's another one of these international whatevers. The measurements one, the one about measurements. They changed the definition of a second from like whatever it was before. I don't remember. Oh, before it was like the amount of time it takes light to travel like 299 million meters, right? Um, but they didn't want it to be dependent on meters, so they changed it to the amount of time it takes a cesium atom to oscillate 9.2 billion times, right? So that's interesting. That is actually the definition of a second, I mean, theoretically in the past it used to be 1/86,400th of a day, but now it is 2 point or 9.2 billion oscillations of a cesium atom. So yeah. But yeah, so basically the atomic clock experiment proved relativity, like it proved it right. It was some experimental evidence because they were like, hey, Vsauce. No, they were like, hey, look at this. The atomic clocks that were on the plane moved slower as if they were in time dilation, just as Einstein predicted. Um,
Ew.
so yeah, and another experiment that kind of proved relativity was like there was a solar eclipse. So scientists they observed they observed stars behind the sun, which not behind, but like right next to the sun, which typically not easy to do. It's not easy to observe stars right next to the sun, especially with a telescope. If you don't want to burn your eyes out, right? So they waited until an eclipse, and then they did this, right? And they noted the positions of the stars, and they were like, "Hey, this is gravitational lensing, slightly," which is kind of like the straight line thing you were talking about, how gravity warps space-time. So the straight path of light was actually bent very slightly by the sun, and we noticed that. And so, yeah, it's great that we can get this experimental proof of Einstein's theories because there are a lot of theories that are sort of nebulous, where they like it's kind of like you have a set of truths in the universe and then you build a theory around those truths. But the problem with doing that is like you can come up with any crazy thing that just fits the specific parameters you already have in place. So, to get your theory validated, what you need to do is, predict things with your framework. So, it's like you have this big like puzzle piece and you fit it into place and now there's like, you already had puzzle pieces before and like some things make sense now, but there are still gaps. And what you have to do is predict those gaps correctly. because if you find new puzzle pieces that don't fit into your framework, then it's gone. And so a lot of theories at this point, they don't really leave room for these gaps, for these puzzle pieces. And it's not intentional. It's just that like we don't have the technology yet, or it's not physically possible. That tends to be a bit of a setback when it's not physically possible. um, but yeah, so you end up with these theories that can't actually be proven, which sucks. uh, but Einstein's theories, they do have experimental evidence, so that's really cool. Because so yeah, that's the atomic clock experiment.
Yeah, the
Uh,
clocks.
Clocks that are atomic, almost as good as a light clock. Anyways, all right. So then we got, oof, this is a bad image. I'm realizing that now. It's so grainy. Whatever. So satellite timekeeping. So GPS satellites actually have to take relativity into their programming. And the way that GPS works, in a nutshell, is that da,
Ba-da-dum-dum.
da, 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 da. Yeah, exactly. Um, so what happens is when you want a GPS, like you want to know where you are, your phone like sends its signal out to three satellites, okay? And what happens is the three satellites, they track how long the message took to get from your phone to the satellite, and that's it, really. They just track how long it took because the message moved at the speed of light, which is a constant. Um, so, since they have, then they get three values of speed. Oh, and they also, a GPS satellite knows its position as well. So we know where these GPS satellites are. So we get three sets of distances from three positions, and that is called triangulation. Yeah, if you know about that, that is triangulation. So we, yeah, triangulation. We know, we find out where you are in three-dimensional space using three positions and three distances from those positions. Because imagine each distance value pretty much creates a sphere around this satellite where you could be. And when you have three intersecting spheres, it gives like, well, I think it gives a couple positions, but like some of them are in space. So the only one that's on Earth, the one that makes sense, there you go. That's your location. So it's pretty cool. Um, but yeah, so since GPS satellites, they're moving so fast around the Earth, and again, these aren't relativistic speeds. You're not gonna like, I don't know, if you sat on a GPS satellite for a year and you came back, you wouldn't notice anything. It would still, a year would have passed. Um, but it's slightly off. So it's moving fast enough, and GPS needs to be precise enough that this actually comes into effect. So the GPS satellites are programmed to run their clocks a little bit fast from their own perspective because they are slowed down relative to the Earth. So after one day passes, from their perspective, a little bit less than a day passes. So we need to adjust their clocks so that a little bit more than, or wait, sorry, so that one day, like 24 hours, 24 of their hours pass in slightly less time. So GPS satellites have clocks that are intentionally running a little bit fast. And if we didn't account for that, if we just used normal Earth clocks on the GPS satellites, then GPS, I think I read an article where they said like it would use, or like it would lose its utility in like 2 minutes. It's crazy how fast these things uh, like get off. And so yeah, it would just kind of, it would like 10 kilometers off every day, I think it is.
Yeah,
So relativity is important. And this is just further proof of relativity if you think about it. Even though it isn't an experiment meant to prove relativity, the fact that we have to adjust for this, like, validates the theory even more. So yeah, that's satellite timekeeping.
there you go.
Yeah. It also means that the people on the ISS, they did like the twin thing, right? It's really
Yeah.
interesting because the twin that was on the ISS is now like 50 seconds younger or something than the twin that was on Earth, or maybe 50 seconds older. I forget because basically when you're in a satellite, you increase your time dilation due to speed, but then you decrease your time dilation due to gravity. So, you know, it depends which is more. So,
Speaking of twins,
hmm. Oh yeah, twins paradox. But yeah, it's interesting because they're not really twins anymore if you think about it, because they are now different in age. Well, they're different in age by 50 seconds,
they're
and I
still
guess,
twins.
yeah, I know. I know, I'm just kidding around, but like, they're,
You have beclowned
I have
yourself.
beclowned myself. I got that word from this, I was just watching this one YouTuber. I was watching this one YouTuber and he said that, and I'm like, this is the best word, I'm using it. So yeah.
My
Um,
favorite word is still outfoxed
Outfoxed. That is a
because
pretty good word.
the qualitative factor could either be you have more foxes than them, you are more of a fox than them,
Huh.
or anything else regarding
More of a
foxes
fox.
as the
Or it could be
qualitative.
cunningness, right? Like
Yeah,
the
yeah, that's why.
fable version of a fox. I have outfoxed you.
Yeah.
Or maybe there's a new maybe you could have a new definition that has to do with like the Fox TV channel. I have
Mhm.
outfoxed you. I don't know what that would even mean. I don't know. You watch
Gaslight you
Fox.
harder.
Yeah, you watch Fox more, so you outfoxed someone. Anyways, yeah, all right. Paradoxes. So these are resolved paradoxes.
I was gonna make a Latin proverb for you, but
Oh yeah.
beclowned doesn't even translate into Latin.
Beclowned doesn't translate into
Let me
Latin.
translate beclowned into English.
Uh, anyways, I should get a big red stamp that says resolved paradoxes because these paradoxes are resolved. But they were paradoxes briefly, but now we're like, yeah, no, there's solutions to these. Don't call it a paradox anymore. But yeah, so we start with the twins paradox. Um, and so this is basically the special relativity uh, incompleteness problem. That's kind of what this is. So say that one twin is on Earth, and the other twin, what
Sorry.
is it?
I translate beclown. I look up the definition of beclown, how it's defined. It says to make a fool of oneself,
Make a
right?
fool. Yeah.
I translate that into Latin, and it's
Okay.
"Fere stultus est," right?
Okay.
And then I switch that back into Latin to English, and all it says is "do stupid,
Do stupid.
do stupid."
That is a great Latin motto. That's even better
Right?
than the scientitia, whatever. The knowledge not written is knowledge lost. Um,
Yeah.
do stupid.
Do
So
stupid.
good. That's gotta be like, oh, that's hilarious. That's like a club. That's like a nerd club. Like that's their motto. Do stupid. Anyways, so the twins paradox. We set it up. One twin is on Earth. The other twin, like flies to Alpha Centauri at a large fraction of the speed of light, and then they return home, right? So they go like 8-ish light years, okay? Um, and let's say they're moving at a speed such that their time dilation is like a Lorentz factor of 2. So when they get back, half the time should have passed. And say that's like these numbers aren't going to be accurate, but say the twin leaves for 10 years and then comes back, right? So, from the perspective of the twin that stayed on Earth, the twin that stayed on Earth is thinking, okay, I know how relativity works. So, my twin, they're going to go and then they're going to come back in 10 years, but they are only going to be 5 years older, and I am going to be 10 years older. Um, but the twin on the spaceship is like, nah, I am actually staying stationary. It is you and the entire universe that is moving at this fraction of the speed of light away from me. So when I get back to Earth, I will think like I will think 10 years have passed and you will think 5 years have passed. So then it actually happens, and then they get back to Earth, and the question is, oh, which one is right? Who is going to be older when they get back to Earth? Um, and the answer is that the person with the Earth perspective is correct because, again, general relativity. They never accelerated, whereas the person that's traveling a significant fraction of the speed of light had to be accelerating for probably like a year at 1g to get up to that speed. So yeah, that's the answer. The answer is that because of acceleration, the twin on the spaceship will be the one experiencing time dilation and will come back uh, 5 years older, and then the twin on Earth will be 10 years older, and they'll be like, wow, amazing. This is so peculiar. Anyways, so yeah, that's the twins paradox. Then we get the relativistic train paradox. I don't know if that's the official name. I'm just calling it that because it's also the pole barn paradox, but I would rather talk about a train than a pole and a barn now. So, okay. So the question is, a train like goes through a tunnel, right? And the train is longer than the tunnel, right? So, and I think it's like both doors of the track or both doors of the tunnel open at the same time and then close at the same time. And the question is, can the train be entirely inside the tunnel with the doors closed? And the obvious answer is like, well, no, because the train is longer than the tunnel. But if the train is moving at, look at that, 0.8 c, so it's moving at 80% the speed of light, the train has been contracted. So it can actually fit inside of the tunnel. So the tunnel is able to close its doors and then open them again, and the train is able to, like do its thing. It won't crash. But then, uh-oh, we look at the perspective of the train. And from the perspective of the train, again, inertial reference frames, the train's frame of reference is just as valid as the tunnel's frame of reference. The train thinks the tunnel has just gotten even shorter, right? So there's no way that the tunnel's doors would be able to close at the same time with the train inside. So then again, it's paradox. What happens? Ooh. Uh, so this is a bit more of a complicated one. And it's actually very interesting. It has to do with the space-time diagrams and the Lorentz transformation. Um, so from an outside perspective, the train is contracted, the doors close and then open. So that's all right. That works. But then what happens from the train's perspective? So from the train's perspective, the front door closes, then opens, the train travels through, then the back door closes, then opens. And you might be like, what? I thought they opened and closed at the same time. Well, they do open and close at the same time if you're looking at it from the perspective of the tunnel. But because the train is on this slanted world line, what happens is as your world line like begins to slant, um, like units of space become units of time. So because the tunnel doors are on two different ends of this tunnel, and because the train is on this world line, what ends up happening is that events that would be at the same time are no longer at the same time when you do the Lorentz transformation. And that is like the craziest one. So I think that's pretty cool. So yeah, that's the relativistic train
The
paradox.
strangest thing.
Strangest thing, right? It's so strange. So yeah, all right. Let's go to the next. In the future. So now we're going to talk about relativity and how it might affect things in the future and how we might have to handle it, what we might have to consider in the future as future people. So yeah. All right, Interstellar Travel. I like this picture.
It's a good picture.
Uh,
It's not a picture. It's a painting. It's a picture of a painting.
wait.
Or is it a painting of a picture?
Wait. I never said it was a photograph. I said it was a picture.
It's true.
I'm pretty sure a picture doesn't have to be a photograph, right?
But the zeitgeist, Max.
But the zeitgeist. Yeah, no. I'm gonna get the definition. I'm gonna be a semantics person. No. I hate it. I hate it when there's like Picture definition.
A
Okay.
painting or a drawing. Okay.
Yeah.
Okay.
Yep. A painting or drawing.
Okay.
So yeah,
You got
that's
me.
I
You
got
caught
you.
me red-handed.
What have you done, Sebastian?
Oh,
There
you
is a verb.
figured me out.
There is a verb that you have done to yourself.
Oh no.
Say it.
Don't say it.
Say it.
Don't.
Sebastian, you have beclowned yourself.
So it was fall over my shirt.
Anyways, yeah, this is a nice picture, but just like last time with the Crusades picture, the website that it comes from is strange. Um,
Oh yeah.
so last time with the Crusades picture, there was a weird church event with the Crusades, which is like inappropriate, I would say. But this comes from like a conspiracy website that like aliens are here. But it is a good picture, so I will use it anyways, okay? But aliens are not here, all right? Let's just make that clear, okay? Um, and yeah, they probably stole it from someone else, so it's fine. Anyways, yeah, interstellar travel. If we move at a significant fraction of light speed, then we're going to have to deal with time dilation. And it depends because with this picture, what this picture seems to be depicting is like a sort of a generation ship. And a generation ship wouldn't be moving at relativistic speeds. It would be moving fast, but like not too fast, right? So it would take like 1,000 years to get to the next star. There would be very little time dilation there. But say that this ship was moving at 99% the speed of light for the journey to Alpha Centauri. Okay, so from our perspective, it would take a little over 4 years to get to Alpha Centauri. But from their perspective, it would take 4/7 of a year because of their Lorentz factor of 7. So it would take about 6 months to get there from their own perspective. So they wouldn't need like as much food. They could bring, it's crazy, they could bring 6 months worth of food, get there 4 years later, and be fine. It's like a riddle, you know. An expedition goes out with 6 months of food. They arrive at their destination 4 years later. Nobody has starved. How is this possible? Do, 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 do. I am the sci-fi sphinx. You must answer my three riddles. Um, but yeah, so this is just kind of interesting because what it means is, well, it's interesting because I'm just gonna keep saying it's interesting. Um, but say that you're moving at like 99.99999% the speed of light, and you take a trip across the galaxy, 100,000 light years across the galaxy. 100 years pass on Earth, right? And then you get to your destination, and a week has passed on your ship. That's how fast you're moving. There is no limit to time dilation. It can be any ratio you want. You just got to get closer to light speed. So you get to that planet, right? You spend, say, a few years there, and you're like, okay, this is boring. I'm gonna go home. You return home 200,000 years later, even though you only like took a trip that took 1 week, then you stayed on the planet for a few years, and then you got home, and that took a week. So yeah, 200,000 years would pass at home. Everybody would be dead, for like generations and generations, right? Like, you would know nobody. In 200,000 years, it's just crazy what could happen. I think 200,000 years is like the amount of time that humans have existed, right? Um, I think it's like from like,
Way less, right? Isn't it only like 20,000?
well, it's actually it's 6,000. Just kidding. Yeah. No. I think it's like it depends on what you consider human. It's like I think it's modern day intelligence levels. I think is 70,000, but I think the human species is like 200,000 years. Like what would still be the same species as us today is 200,000 years, I think. So you would get home, right? And humanity could have evolved into or probably would have evolved into an entirely new species. I mean, think of how fast, like, think of Old English, right? That is unintelligible, and it is only 1,000 years old. Now, 200,000 years is like that amount of time passes, right? like verbal communication could be dead. Like there's no telling what would happen in that amount of time. And from your perspective, it was only like a couple of years, which is like crazy. So that's the effect interstellar travel can have.
They only use slang words.
Oh, they
Like
only use slang words? Oh no.
me am have big sad, big oof.
Oh no, stop. I'm finna blah
Yeet
blah
my
blah.
beans. I'm finna.
This is
I don't
lit.
know.
This is lit, fam. Oh god. Imagine if you got home and they talked like that. It would be like that's got to be the dark twist ending to some movie. Um, but yeah, so that's the interstellar travel aspect. I think that's yeah. All right. Anything else to say on this? Yeah, we only have a bit of time left. Okay, black holes. So interstellar movie. I like
Movie.
I like this movie. I know a lot of people don't like it, but I kind of like it. So sue me.
It's a sad movie.
Yeah, yeah, it's a good movie. Sad. But yeah, when you're close to a black hole, right? That's
Birthday Dad. I don't
birthday
know why that
dad.
went through my head, but
You'll laugh, you'll cry, you'll birthday dad.
yo, Birthday Dad. And
Anyways,
he misses all of her birthdays.
yeah. Oh yeah, he misses all the birthdays.
He's the worst
He's the
birthday
worst
dad.
birthday dad. Yeah. He only comes back for her death day. So black holes, right? When you're close to a black hole, the amount of gravity it has ends up warping time and slowing time. So say that there was like a planet. I have an actual story concept for this, and it's like I'm forgetting it's like the immortal worlds or the eternal world, something like that, where there are planets that have intentionally been placed near a black hole so that like if you don't want to deal, I don't know, for a few years, if you're like, yeah, this is boring, let's see what comes up 30 years later, you can go to one of these planets, take a vacation for like a week, and then you come home and it's 30 years later. Kind of like what happened in Interstellar, the movie. So I mean, not at all, but like on a very basic level, what happened? Like none of the character motivations are correct, but on the basic level, plot synopsis, that's kind of what happened in this movie. So yeah, that's interesting. That's an interesting thing to take into account. That when we deal with these massive black holes that are strewn about the galaxy and the supermassive black hole in the center, like how are we going to deal with that? How are we going to deal with all this gravity and how it messes up time and stuff like that? I think it's interesting. So yeah, that's all I have to say here. Uh, yeah, should we restart? We should restart the meeting.
Yeah, and we'll do final thoughts.
Yeah. Oh, that's it. Oh, nice. This was a nice little.
Yeah.
I am. Oh, I am so ready to go to sleep. Okay. So yeah, we'll see you guys for final thoughts. Okay. Um. Okay. Participants. Oh, yeah. Invite Sebastian. Right. Pose now. Okay. All right. All right. We're back.
We are.
Yeah. Such a good word though, beclowned, right? All right, let's get into final thoughts. Okay, final thoughts. So, what do we think? I think that I am incredibly tired and stressed, and this is not going to be a fun week.
This is the final push, Max,
What is the final push for what?
for after school. You're pushing through the lines.
Oh, that's true. That's true. Yeah, if you think about it, I'll be very stressed this week, and then I'll be done for like 2.5 months. And then we do it all over again. The never-ending cycle, the eternal story. That's all that we do.
Why
And
are we here?
why are we here?
Just to
No.
suffer.
Existential crisis time? We should do an episode on existentials. Wouldn't that be an interesting?
This is my new tweet. Is it going to be mirrored, or is it?
I cannot. I can't see it.
You can't see.
What does it say? Just say it. Here, wait. Are you not allowed?
It says just streamed with 2 E's
Okay.
with cavity max spelled MACKS.
Horrible, but also wonderful. Uh, yeah, so final thoughts. Relativity is such an interesting concept. I love relativity. It's like a fun thing to put in a sci-fi story. Um, Unfortunately, as with any science concept in sci-fi, it always gets misinterpreted. They're like, oh, if we can blah blah blah. I'm like, don't test me, please. Do
Was it?
not.
I might be wrong, but in the very first Planet of the Apes movie, like not the recent ones, there was like one back in, I forget what it was, either the 90s or the thousands. But the plot of it was astronauts went up near a black hole and they didn't understand like relativity or something, and
Yeah.
they and the planet was inhabited by monkeys.
Yeah, I think that was the plot. I do remember that. It was a time dilation thing. Um, but then future ones just got like plain into time travel. That movie has been remade so many times, you know. I thought I was watching the original, like I was because it was like I saw this old movie like on TV and I'm like, oh, this is the original Planet of the Apes. Nope, it was a remake and it was very old. And so
Dawn
there's
of
so
the rise of the planet, of the beginning of the
oh
end,
yeah, Dawn of the Rise, the beginning of the start.
of the planet of
Oh gosh. But yeah, anyways, relativity is fun. Sometimes it gets misinterpreted in sci-fi, but you know what? That's okay. As long as we got as anything that increases scientific literacy, and makes people interested in science, that's good in my book, right? So yeah, no guests this week, but I thank you all for watching. Let's see. Do we have any more comments? Let me make sure I didn't miss any.
we do not.
No comments? All right. Well, thank you all for watching, and thank you, Sebastian, for being my co-host as always.
Even though I've beclowned myself, I feel welcome.
Even though, yeah, don't worry, I've beclowned myself many times on this live stream, so it's okay. But yeah, that's it. Thank you guys all for watching, and I'll see you next Sunday when I am like 99%
Happy.
dressed.
When I get
Bye.